Hello everyone, thank you so much for joining us for our webinar today. Let's go ahead and get started. So today's webinar is how final element proof tests can affect your safety instrument functions, or your SIFs. And this really came from a recap. Exeter was at the ISA Energy and Water and Wastewater Show last week in Orlando, and we presented on both proof testing your final elements and on cybersecurity, and both were very well received, and we wanted to take that information that we shared at those conferences and share part of it with you today here as well. So we will be sharing the proof testing your final elements and showing how your proof test effectiveness can affect your SIF. For those of you that have not yet met me, my name is Lauren Stewart, and I am a CFSE here at Exeter. I work with a lot of our mechanical customers, helping OEMs achieve SIL certifications for their devices. I also work with Exeter Academy, doing a lot of our teachings and trainings, along with a bunch of these webinars and blogs. But the reason you're here today, we're going to be talking about proof testing. Proof testing is a super important part of the management of your functional safety and how you manage your safety instrumented functions, or your SIFs. It's an activity that is required by the functional safety standards IEC 61511 and 508, and because of that, more and more end users are implementing proof tests. But with that, there's confusion. A lot of people don't know what should be included in a proof test, what that proof test coverage should be claimed as, and there's some gray area. So hopefully this webinar will clear up a lot of that gray area. We're going to start this presentation by defining what exactly a proof test is, starting at the very beginning, defining it, and seeing what all goes into a proof test, what the real objectives of proof tests are and why. We'll then go into proof test coverage, why it's such an important safety parameter, and explain what it is, how you get it, what's calculated from it, and show some real life examples. For those of you that are not yet familiar with Exeter, I wanted to welcome you. We are involved in functional safety, alarm management, and cybersecurity through the complete supply chain in functional safety. So whether you're at the very beginning, making devices that go into the safety systems, those OEMs, we can help get you SIL certified, we can train you, teach you, and we have tools that make your life easier the whole way, people designing the SIFs, doing the calculations, the whole way through to the end users using those SIFs and pieces of equipment, maintaining them, and doing proof tests. So whatever you need with functional safety, security, reliability, and alarm management, we have people to help you out no matter what area in the supply chain you are. I also like to point out that we are a very global company, and this map isn't even have our most recent additions on it. I need to update it. I like to say no matter where you are, where your customers are, where your devices are coming from, we have experts close by to help with all of your functional safety, alarm management, and cybersecurity needs. And then the last brag slide about Exeter, I like to let everybody know, as you're on these webinars, so you know a little bit about us educating, but I like to say, and excuse my pun, that we are an open book. Everything that we research, everything that we teach, everything that we do here at Exeter, our processes, our procedures, they're all documented in books, white papers, blogs, webinars. We go to conferences. We get that information out through speeches. Whatever we are researching and finding to be the most safe and the most accurate, we want to get that message out. We don't want to just hold on to it. So always come back and check out our books. You know, these webinars and blogs are always free. Download our white papers and get the most up-to-date information on functional safety. But let's get to the reason why you're really here today, how final element proof tests can affect your safety instrumented functions, or your SIFs. So as I told you at the beginning, we are going to start with a completely clear slate and define what a proof test is. A lot of people might have a preconceived notion in their head what a proof test is. However, let's break it down. So the main functional safety standard, IEC 61508, talks about a proof test being a manual periodic test performed to detect dangerous hidden failures in safety-related systems. So if necessary, a repair can restore the system to as close of an as new condition as possible. So you might be thinking that's a little bit different than what a definition of a proof test you might have in your head originally. Most people are thinking a proof test needs to check that functionality of the SIF, make sure it's going to do its job. However, if you have things like automatic diagnostics already checking for things, you don't want to recheck for things or issues or failures you've already know are not there, you've checked. So here at Exeter, we wanted to take the IEC 61508 definition and expand it, clarify it a little. So we agree with all of what it's saying, but say the purpose of the proof test is to detect any of those failures not detected by automatic online diagnostics. The dangerous failure, diagnostic failure, parametric failures, to detect unauthorized program changes. So when we are talking about a proof test, we want to consider what those possible dangerous hidden or dangerous undetected failures can be, and how can you design a test to show those or to expose those dangerous undetected failures. As I mentioned before, if you're automatically testing or checking for different failures with your online automatic diagnostics, don't waste your time and your money rechecking, revalidating, retesting what you already know works. So now that we know what a proof test is and what it really needs to do, find those hidden or undetected failures, now we need to think, what does it really need to do, and how can we design a proof test to go along with that? Well, it can be broken down into two main requirements. Your proof test is going to need to have functional requirements. What exactly does that SIF need to do? Does it need to close off flow by shutting a valve? What functionally does that SIF need to respond in that safety function? And then after that, you need to look at what are the performance requirements. Things like, well, is leakage acceptable or not? What are the timing or response requirements for the SIF? And things like that. Those, depending on your situation, your plant, your SIF, leaking may or may not be an issue of concern for you. Once again, depending on where you are, what you're doing, timing. That process safety time might be a very critical point in your functional safety management. However, in some cases, it may not. So take a look at what the performance requirements are for your SIF and what's required. A good example is a final element might need to close to class 3 leakage, which is allow some leakage, but do so within 180 seconds. So that would be the performance requirements. It's saying, well, as well as the functional. It's saying it needs to close, it needs to allow a little leakage, but not very much, and has to do so within 180 seconds. Always, when designing proof tests, look at the safety manuals for each device going into that. All those safety manuals will list any sort of exceptions to the rules. If there's a sort of environment or operation that's not able to be handled by that device, it will be listed in the safety manual. So always double check that your performance and functional requirements don't get invalidated with any of the safety manual exceptions. Once again, think about when you're designing your proof test, you want to design for those failures not detected by automatic diagnostics. Once again, think how it can work functionally and performance-wise, but not waste your time already proving and testing what you know works, and instead design a test that looks for those undetected failures that your diagnostics are not already checking for. But why does this all matter? Well, yes, doing a proof test to check the functionality of the device is good, but it's really so much more than that. Remember, the real objective is to detect those failures not detected by automatic diagnostics. And that becomes a big deal when it comes to your SIL calculations, such as your probability of failure or your PFD average. Those SIL calculations want to look at that risk reduction possible. One of the main functional safety equations used in that risk reduction for a SIF is the PFD average, or the average probability of failure on demand. And it's a really long, drawn-out equation with a lot of different variables in it, but it considers what are the probability of failing. And it actually, of its 9 key variables, there are 3 variables that deal with proof tests. One being the proof test duration, another being how effective or how often they're done, and then mostly how effective are your proof tests. We're not going to spend much time on the proof test calculation. Just wanted to show, or PFD average calculation. I just wanted to show you a couple of the key variables here showing the proof test duration, interval, and proof test coverage. So knowing that these numbers go into this equation that can determine risk reduction, but what is the bigger picture? That long drawn out equation actually goes hand in hand with SIL tables in the standard. So in IEC 61508 and IEC 61511, there are tables equating PFD average ranges with a safety integrity level, or a SIL. So that calculation is directly responsible for a portion of what makes a device SIL compliant. It's one out of the 3 compliance requirements from IEC 61508 and 511. To meet full compliance, you need to also consider the SIL capability and the architectural constraints, but the PFD average is one of the 3 main barriers or main requirements to achieve a safety integrity level. So as you know, having that safety integrity level for a SIF is a big deal, and having your proof test coverage and information in that calculation can be a big deal as well. But what does this all mean? Often when we look at proof tests and proof test assumption and PFD average calculations, often we see that the proof test coverage is assumed to be 100%. You did the proof test, well, that means everything's tested, right? Well, stop for a moment. Was everything tested? Let's think here. Let's take an example. A proof test is done. You have your SIF. You're going to isolate your sensors, and you're going to pump it up so that the pressure points exceeds the trip point. You have somebody go and observe that your remote actuated valve moves. Are there any potential failures that could still be hiding? Well, no one checked out any of the internals of that valve? Were there damaged seals? Was it seated properly? What about the butterfly or the ball itself? Was that damaged and working properly? What about the shaft? You might not know things like leakage or timing. If it wasn't timed, how important is that process safety time? What else could have gone wrong? Let's see. Well, you artificially pumped up the sensor, so what about those process connections? They could be failed. What about a power supply droop or a wire resistant? It could limit some current. That could disable alarms or diagnostics. So you might think, well, I did a proof test, I observed the valve moving, but there are a lot of dangerous undetected failures still creeping around in that proof test. Was it perfect? Was everything tested? I always learn best from real life examples, so I want to always add some in to my presentation. So I wanted to look at an example of a high protection SIF, and I put numbers that we see often, saying we have a SIL3 sensor, you have a level transmitter, logic solver, remote actuated valve, you have your solenoid valve, Scotch yoke actuator, certified ball valve put together to make a beautiful system. You're going to say you have a mission time of 5 years. You're going to proof test the sensors and final elements every year, and the logic solver every 5 years. You, like we've seen before, proof test coverage 100%. You did your proof test, it worked right. And you're doing the proof test done with the process offline. So I put these into our Excelencia software. It kind of does the PFD average calculations in the background for you. And as you can see, it gave us a PFD average for our sensors, our logic solver, and our final element. And we got, let me get a little laser pointer here. And as you can see here, we ended up at a PFD average of a SIL2 with a risk reduction factor of 147. That's not too bad. Now let's look at everything exactly the same, but let's use a little more realistic numbers for our proof tests. First of all, that proof test coverage, instead of 100% for everything, we're going to be realistic and say we're 90% for a sensor. Those final elements are more like 70%. And we're going to actually do the proof test 2 hours with the process online. Everything else remains the same. This time, you can now see we still have our PFD average for our sensors, our logic solvers, and final element. However, we were knocked down to a SIL1 on our PFD average here. Not only that, with a risk reduction factor of 17, it's barely making a SIL1. We're just barely squeaking by. So the chances are, if you need to be a SIL1, most of you wouldn't be covered. It's only a small percent that would actually be covered by the SIL1 SIF. So that's an extreme case. However, just being unrealistic or overly optimistic with your proof test coverage can really affect your safety. Once again, I'm a very visual person, so I wanted to see what this looked like visually. So as time goes on, your probability of your failure, or your PFD average, is going to increase. So as time moves on and the mission time of the plant goes on, you're going to increase your probability of failure until you get to some certain point here. Then all of a sudden you decide, oh, it's a good time to do a proof test. And if you do your perfect proof test, we know that there are 0 undetected failures left. It found everything. If that is the case, your probability of failure is 0. You found everything. You know it worked perfectly. Then you start the climb again. Because everything was perfect, it starts almost brand new. And you continue up, building probability as time goes on until you decide it's time to proof test again. Boom, you do another perfect proof test. You know there's no failures, or you repair it, you get back up online, you continue the cycle again. However, we know now, chances are you aren't doing a perfect proof test. Are you finding every single possibility of failures out there? More realistically, we're going to be looking at an imperfect proof test, or a realistic proof test. So once again, as time goes on, your probability of failure is going to increase. And this time, as we increase, we're going to get to a certain point, and we're going to do a proof test. This time we know, instead of being perfect, we might have a proof test coverage of 80%. We might find most of those hidden failures, but not everything. That time, you're going to start at this point, and the probability of failure will grow. Now, as you can see, each proof test will get a little bit higher and higher starting point. And that might not be a big deal, your first or your second proof test, but as the mission time goes on, that could creepingly get to a big deal. As we know, the standard allows you to take the PFD average, because you don't know exactly when in this time a failure could happen, so you take the average of it. The first proof test period, we're going to have a PFD average right around here. That PFD average would stay the same if you're saying that you do a perfect proof test and it comes right back down. Those spikes would look more like the last slide. However, we know that each proof test, you're not at 100%, and your PFD average is going to creep up each proof test. When you look at the PFD average for the mission time of the SIF, this one being a 5-year, we're actually up here instead of the PFD average for that first. This would also show you the difference of assuming that perfect proof test, or 100%, compared to that more realistic, or 80 or 70 or whatever it is calculated in this example. What does that mean in real life? Well, as you can see, your first 2 proof tests, you're operating in a SIL 3 protection area. You're reducing that much risk. However, in proof tests period 3, 4, and so on, you're actually realistically operating only at a risk reduction of a SIL 2. That could let you think that you're reducing a lot more risk from your system than you actually are. That could, I call it, lead you to be kind of like an ostrich sticking your head in the sand thinking you're protected and nice and cozy, when in reality you don't have that nice safety cushion you calculated. So how do you accurately measure your proof test effectiveness? Well, one of the most accurate methods of predicting proof test effectiveness is to review all of the components in a product, look at their failure modes, and record or test each particular manual proof test. Will that proof test detect each component failure or not? Exida does this instead of doing the test like the end users could do. Exida does this with pencil and paper during the FMEDA process, or the failure mode effect and diagnostic analysis process. What we do at that point is we look at a cross-section of whatever device that is, say a ball valve, and we'll look at every single portion of or in part on the BOM. Each seal, each nut, each bolt, the ball, the stem, every portion. How can it break? How can it bind? How can it stick? How can it leak? What would happen if that did? Would it be dangerous or safe? Would it be detected by those automatic diagnostics, or would it be those hidden failures? At that point in the FMEDA, we can look at each proof test and say, well, if I do these steps of this proof test, how much of those dangerous undetected failures, how many of those would actually be found? And that's going to be your proof test effectiveness. It's going to be that percentage of those dangerous undetected failures. Because it's a percentage, it's a range from 0 to 100. However, both of those are highly unlikely. It's typically between 40 and 90%. Your sensors, your logic solvers will be on that higher end, where your final elements are going to be on the lower end. It should be understood that manual proof tests are done once again to detect those failures not detected by automatic diagnostics. Don't waste your time, don't waste your money reproving what you've already know. Test to detect the same failures as automatic diagnostics. Just increase your cost, increase your downtime, and accomplish very little. What you need to look for are those hidden undetected failures. With that, usually, if you have a better automatic diagnostics, you're going to have a lower proof test coverage. Well, what does that mean? How does that work? Well, let's look at an example again. Let's look at two products. They are the same. They both have 100 fits. Fits are a failure rate, failure in time. It's 10 to the negative 9, in case you're unfamiliar with it. But 100 fits of dangerous failure rate. And both products use the exact same proof test. However, the two products, product 1 and product 2, have different automatic diagnostics. Product 1 has poor automatic diagnostics, while product 2 has really good automatic diagnostics. Because of that, they have different proof test coverages. Product 1 with the poor automatic diagnostics has a proof test coverage of 80%, and product 2 has good automatic diagnostic coverage with a proof test coverage of 20%. Sometimes when people see that proof test coverage that high or that low, they automatically assume one is more reliable or that's the one they should purchase. However, take a moment and think what that actually means. That proof test coverage is how many undetected dangerous failures there are. So if your automatic diagnostics are finding those, it might be better off in the long run. So product 1 both had 100 fits, where the product 1 automatic diagnostics only found 10 of those fits. So 90 fits were still undetected, or those dangerous hidden failures were still 90 fits. The manual proof test, it was 80% proof test coverage, so it's going to detect 72 of the remaining 90 fits. However, that still leaves 18 fits undetected. Those are those dangerous, undetected, lurking in the shadows still. On the other hand, you have product 2 that had those really good automatic diagnostics. It found 90 fits and only left 10 originally. That manual proof test, it was okay. The proof test coverage was only 20%, but it found 2 of those 10 fits remaining, which only left 8 fits undetected still. So don't always go off of what proof test coverage, how proof test coverage means for each for kind of your measure of quality for a product. Kind of almost the opposite is true. So how do you determine this proof test effectiveness? Well, I said earlier you could design the tests and test for each failure mode and find out which dangerous undetected failures would be found, or it can be done through an FMEDA process. Establishing a baseline for each device, going through that FMEDA and with each failure modes and how each test or diagnostics would be covering each failure. At the end, all of those different dangerous failures are allocated between, was it found with diagnostics, was it found with proof tests, or is it still hidden there? There are different levels of proof tests that can be achieved. And if you think about it, that just makes sense. The more work you're going to put into your proof tests, the more of those dangerous, undetected failures will be found. This is an example for, let's just say, a floating ball valve. For a floating ball valve, we could first do a partial valve stroke test. That partial valve stroke test might find you might move the valve 5 to 10% of its total stroke. That stroke might prove that the bonds of sticking aren't there, that things can actually move, that the shaft is still connected and can still turn that ball. However, there are still a lot of those dangerous undetected failures still lurking in that if you just move it just a tiny 5 to 10%. The next kind of, I call it almost an order of magnitude up. So your next level of proof test would be doing a full valve stroke test when you're fully opening and fully closing that valve 100% of that stroke. Then another variation of a proof test could be a full valve stroke test with that leak test. Once again, that leak test could find more of those hidden, dangerous, undetected failures. Usually, that full valve stroke test with a leak test, once again, would be done during a downtime or turnaround. So a different variation could be proof test 5, doing all of that except at operating conditions. Now, I know not everybody can do all of these 5 proof tests. There are many conditions and operations that you cannot do a full valve stroke test, or you cannot do any proof test during at operating conditions. There's times where it's not going to be possible to do a leak test. However, just being aware that there's different variations of proof tests and thus different coverages associated with a proof test can be helpful. Maybe you only can do a partial valve stroke test in your operation. However, just know that the effectiveness of that is not going to be the same level as a full valve stroke test at operating conditions with a leak test. And these might be things that you can even switch up and do both or multiples. I've seen people do that partial valve stroke test more often or every so often, maybe once every 6 months, or where they do a full stroke test once every turnaround instead. And they know that their proof test effectiveness and the proof test coverage for each scenario would be different. Once again, I really like examples, so I wanted to take some numbers and put them into and put them into real life cases and real life SIF. So I put together just a pretty simple SIF. We have a solenoid, a poppet valve, an actuator, a valve, and some of the accessories put together. And we did FMEDAs for all of these cases. As you can see here, this is that dangerous total failure rate, those hidden failures lurking in those dangerous undetected failures lurking there. While we were in the FMEDA, we considered the different proof tests. Proof test 1, remember that it was just that partial valve stroke test, that 5 to 10% of the move. As you can see here, it found some of the dangerous failures, but there are still a lot there. Let's look at the valve, for example. We were able to find a good portion of those failures. However, there were still 315 dangerous, undetected failures lurking after just a partial valve stroke test. As you can see with that proof test, just that little bit, and this is for those, remember this is just an example for these specific devices, but that partial valve stroke test only found about 57% of the dangerous undetected failures. And proof test 2 was that full valve stroke test, that 100% opening and closing. As you can see, it found more, but there's still a lot lurking there. Proof test 3 is that full valve stroke test at operating conditions. That's going to take another jump lower. But as you can see, between proof test 3 and proof test 4, there was a major jump, especially in the valve actuator failure rates. That is when we added that leak test involved. So all of those failures due to leaking were then, instead of being undiscovered, they are now discovered. And then finally, we have our proof test 5, basically throwing everything at it. We're doing a full valve stroke test at operating conditions and at leak test. As you can see, it found almost everything. There were a few dangerous undetected failures still lurking in some of the devices. However, it found almost everything. So in summary, just wanted to hopefully clear up some things about proof test coverage. Whoops, sorry about that. Hopefully clear up some of that gray area. Explain that just assuming the 100% proof test coverage isn't going to be your best approach. What you doing realistic proof test calculations can impact your SIL by an entire level, and not knowing what you're actually running is, as I said before, kind of like an ostrich, just putting your head in the sand, hoping things are going to be okay when you're not using realistic numbers. At this time, I think that is all of our questions. If you have any others, please let me know. And check out our more white papers and books and webinars to come. And thank you for joining us.